where are we in the proof? So Nick's talk this morning basically finished. So the first day we favored GLC1. Nick's talk today finished GLC2 modulo another talk of Lynn, which will be kind of supplementary. And so Justin's talk and the present talk will summarize GLC3. And so basically, like GLC3 has a lot of proofs which we can't cover. And I'll say what I can possibly say about them in this 1 hour. And last day tomorrow will be devoted to GLC4 and GLC5. So that's where we are in terms of the papers. All right. So here's what we want to do. So Justin explained to us that there are functors, Eisenstein functors. Orient them correctly. What's this? And so here we put the second as the same functor. Here we have a Langlands function for G. Here we have a Langlands function for L. And it will be an important part of the proof to show that this diagram can be used. So basically, I prove Langlands equivalence. It has an ingredient which, like this introduction, that's going to sort of we'll assume that you know stuff for related subgroups. But the torus, we know it because it's fully MKI. Then we'll be left to deal with the custom part, which is exactly what we'll be doing for. And not only that, so we won't show that both the diagrams to use this Eisenstein functor and this constant term, which was expressed. So we won't show that this diagram can be used both ways. So both this one. This and also inductions. All right. So, as I said, I'll try to do what I can to explain the ideas involved in proof of both these computations. It's very distinct. So let's deal with the downward facing diagram with Eisenstein fields. So let me just wave my hands to say the following. So instead of LG, let me write a coarse function. And I'll argue that it's enough to consider limitation for the first time. So what the coarse function. So I need to know how to orient it correctly. Oops. Once this is, I'll call it Eisenstein force. So what we mean is just analogous functor. But of course, you do the same thing. So, and I claim that this is correct. So I want to say, and I claim that if you want to prove the commutation downward facing diagram, it's not to prove the commutation of the diagram. Why is that the case? well, you want to do the computation, you can start with a compact object M and trace its clockwise circuit and anti-clockwise circuit. And I claim that you land in a subcategory in code what is the check, which, well, I claim that in both cases you land in the eventually connected subcategory there. And we know that it's projective form of the quasi-corresponding. So why is this the case? So if you start with a compact object here, we know that Langlands functor sends it to something eventually connected. Prove it on day one, and if you look at just the definition, you'll see right away that the spectrum Eisenstein series functor sends eventually co-connected to eventually co-connected. And similarly, start with a compact object left aside, you can fly Eisenstein functor to the geometric side. This Eisenstein functor admits the right adjoints, therefore it sends compacts to compacts, and so you end up with a compact object here, and the Langlands functor again sends it to something eventually. So you end with the eventually connected subcategory to show that two objects agree, now to project them to quasi-co. So that's why it's something with this guy. So now we'll prove this commutation by a novel trick that it's my most original idea in mathematics. It's proved by the method of Q. So the idea is that nobody has enough attention span to perceive the cube, and people get convinced just out of fatigue.
Proof by intimidation.
No, by the cube. Intimidation is too generic. All right, so what's the idea? So the idea is that, as was mentioned several times, this functor gamma spec in check, in check around, is fully faded. So if you want to show the two circuits commute, it's enough to post-compose both with this functor and show the resulting diagram commutes. And so I have to make this functor. It's always very tricky. Otherwise, people won't get convinced. Yeah, exactly. That's the problem. So so, and this gives us the fact that we compose with functor gives us the opportunity to use the definition of Langlands functor. And the only thing we know about so far, actually, we know two things: how it behaves vis-a-vis Gaitsgory, how it behaves vis-a-vis this functor. And so, or right with G, around this is because so much like the balloons. So far, I only know that of this. Okay, so now with me. I'll put in the diagram and say what they want to say. I'll write red and check one. With this arrow, it's this functor gamma for M check. This one is coefficient for G. And so this will be this. We're discussing which like and this is coefficient for G. All right, and so what do so if you look at it, so what we have so far is this. So, this. These arrows. I just brought a scale. No.
Dennis, people can see those arrows on the side.
People can see. I don't see. You can't see. I cannot see. Oh, just have mercy on the old man, okay? Let me play. Anyways, so what's missing? These two arrows. And let me put them in. So I'll first put in this one. And so what is this arrow? So there is the functor for we check the random effect that was discussed in Justin stock. It's invariance with respect to equal triangle with parabolic. It's a factorization functor. To make the value commute, we have to do a trick like what Lin did in his talk, but it's kind of dual operation to that. So let me say it's kind of Hicks rule. I will not say what it is because it will take us a while. So basically, it's really kind of dual operation of what Lin or what Nick explained to us.
The rationality of the arrow.
Indeed. So it's reduction. It's parabolic induction from you inflate to P and induce to G. It's induction factorization functor. So, and this functor is actually strictly unital, but it won't help us. And so you need to perform some kind of fix. And so I will not explain the nature of the sticks, but basically after some duality mechanism that Justin explained in his talk, so that the last 10 minutes of his talk will tell us that kind of this facet the right facet will commute. So now let's see what we have so far. So we have so what we want to make commute is this bottom lid. So we have the right facet commute. So the front facet commutes. This is our definition of Langlands functor. The back facet commutes. So what we have to do in order to establish the commutativity of the bottom lid, we have to insert an arrow here so that the left lid and the top lid commutes. So need so define a functor and I'll call it co-Jacquet. So from the Whittaker category of and to the Whittaker category of G, so that so the upper lid commutes and left lid commutes. For some reason, psychologically, when I think of these cubes, I always imagine coffins. Once your victim is inside and business. All right. And again, it can be a factorization functor, and again, they apply some kind of fix. Exactly tool to fix last time. Okay, so what do we do? So this customer Schleicher, they were equivalencies, and if we want the upper lid to commute, why don't we just transpose this to here? And again, what I said here, it's really the functor of induction. So we'll make the upper lid commute by definition. So define with your shrink this factorization functor for Jacquet to with your G so that the diagram commutes. So at least then we'll be left with one thing to prove, namely the commutativity of this diagram. The left leg. Which is that?
Like, usually with induction, you grab and check, you had some fix, check, and then what?
Say again. So I'm saying that if you were dealing with a constant term functor,
Yeah.
you will be dealing here not with invariants, but it's some kind of fix that Nick explained, right? It's insertion of good.
Yes.
So here we're dealing with exactly the dual situation. So it's a fix of the dual nature that I don't want to go into. But like if you look at what's happening with Nick's talk, and if you dualize everything, you'll discover what it means. It's a universal procedure.
Okay. But I think just like the fiber of one point. But,
Here.
Yeah. Anytime it's a plane.
So you're forcing me to do what I don't want to do. I'll tell you what to do. So yeah, kind of. You do this and you apply with a jump on one side, going from the entire round category to independent category. So independent category gives. Okay, sorry. Okay, I do want to do the independent category, and it's really if you can mind, you see that operation. It's universal fix that has to do with mass spaces.
Sorry, I knew you already said this, but the right square that shaded in, it's exactly like the came from the square that I showed.
By the odds, right? Exactly by the odds. You know, no difference. Yeah. All right. Okay, so and so we want to show that this can be. So the next 5 minutes will be hands wavy. I want to just kind of convince you the spirit of things of how it's done. I won't actually show how it's done. I want to say what kind of mathematics goes into it. So
it's
pardon me?
yeah, the diagram in here is the code J and the
So coj is like really it's a factorization functor.
but no more with the fix.
So this is factorization functor like induction, but in the diagram, it's not that functor of the level of categories in the round space, rather it's fixed. Remember, like it was Nick's fixed, so you go, there were two factorization categories, C1 and C2, and he explained the C1 rounds. You started with a last factorization functor, and you could do something to it to obtain another functor.
And here is the real code J, not fix.
Again, it's coj is a factorization functor, and it's factorization functor. It's really of local nature, and the fixed is something that happens on the round space. After this, if you start with factorization functor, there's some procedure that produces a cofix, and that's what we do. And I don't want to say what this procedure is, because it's an exercise to figure it out by geometry. From the procedure dual to this. All right, so I want to explain what kind of mathematics is involved with checking that the left diagram commutes. I'm doing it so if you were to go and read the GOC3 paper, you'll know the kind of the spirit thing, so we're a good path. So instead of defining this coj, I'll tell you what actually J is. So J will be pointing in the opposite direction. So this is J. Rep G check. Rep M check. And this will be the functor invariance with respect to. And this is our. Well, it's definitely not definitely like that. Well, that's an equal G. That's the one so I can. So I'll define a different functor. And it's closely related to this coj by some geometry operation that I won't explain, but I want to explain kind of the geometric nature at least some things involved.
Does your prime is street?
It's not prime street.
Is it the same as
It's the same as
category?
it's the same category
You
as
didn't
before.
use street.
It's the same category as we had before. So I'll define a certain functor and then I claim that the diagram commutes. So what's this J functor? It's kind of non-trivial. So what you do is the following. So I'll first define the following functor. So we'll go from root sheaf of group G. Now we'll do something very interesting. We'll take D modules on the affine Riemannian, but we'll put an equivariance condition. It's what we call semi-infinite category. It's like loops into uniform radical. It's convenient to use the opposite parabolic here. For reasons we'll see soon. L plus M. So I'll first describe the functor like this. So here's what this functor is. So I'll draw a long circuit. So first of all, this is equivalent to G, and I'll rewrite this category as follows. It will be D modules from Gur G times Gur M, but equivariant with respect to loops into the entire Gur M. Entire negative parabolic. So the point is that this acts on this transitively, with this being exactly this the stabilizer of the point. So then you forget the equivariant conditions and go to D modules on group G. D modules on group G times D modules on group M. And next thing you do the pairing. So on any in scheme, there's a natural pairing of D modules on the scheme with itself, namely you tensor them up and you take cohomology. It's Verdier pairing. So let's call it G times identity. Go to D mod G. Again, so what you do with this, like I said, functor from this tensor product to that, it's pairing. It will appear a bunch of times today again. Rather tomorrow. Tensor up and take homology.
It's Gur M, right?
It's your own, sorry. The claim is that if you trace through the definition, that you will see that if you start with from here, well, a priori you landed in here, but the claim is that you actually land in the Whittaker category. So with this equivariance condition with respect to the uniform radical of the Borel of M survives. So we messed here with the uniform radical of the parabolic. Here the condition with respect to the uniform radical of Borel for G. We got rid of this, but the uniform radical of the Borel of M survives. So this is this functor. And now, so you use a very particular object, I call it delta minus semi-infinite. It's the dualizing sheaf on Gur M as it's I lower sheaf of the dualizing sheaf on Gur. The unit orbit. So sometimes it denotes by S minus. So S minus is the unit, is the orbit of.
That's the third P.
Pardon?
It's the third P minus.
It's good minus, yes, I should say.
Minus there, good.
Minus degree 0 and I'll is embedding degree minus.
So maybe you will go empty.
Okay, so let me call it S minus. So S minus embedding integral G. And this is the orbit of L and P minus of the function. So it's some very particular object in this category, and now this functor J is you apply this functor where you plug in this delta here. So you just apply this functor with the delta minus semi-infinite being 1 So this is J, and the theorem is that this diagram commutes, and it's the theorem that we attribute to the stiff. The dark side of the force.
Is the so that's the second one diagram order. The same as just convolution administration.
It's not very visible. You take Schritt extension.
No, it's Schritt extension. Even for star extension, that would be the case, but because Schritt extension is much more method.
It's Schritt extension.
If it were star extension, it would be correct. But here it's integration with very non-trivial terms. So, like, if you want to calculate the fibers, suppose, like, sort of, and you have T, you want to know the value of the functor. Yeah, you take the Whittaker sheet, lives on, like, again, let's be P equals P. Yeah, it lives on the n plus orbit against the parameter. Naively, what you said, you want to intersect with the semi-infinite orbit, restrict with the semi-infinite orbit integrate. That's not what you're doing. You're taking this negative semi-infinite orbit, you take the Schritt extension of it, realize a sheet on it, it's something non-trivial, tensor up and integrate. Right. So that's what's happening. Okay. It's a non-trivial functor. And so the theorem is this diagram commutes.
But you probably have some Euler property.
Pardon me?
You probably have some Euler property.
I have ULA.
You.
Well, it won't help you. I mean, it's really non-trivial curve. Okay, so when I said that I transfer this induction to the left-hand side, so saying these words will not help you. You have to give some kind of geometric description of the functor, and a closely related functor, which is this functor of invariance, has been described here. So it's this procedure. So after this, you have to confront geometry. You really have to show that the left facet here commutes. Let me just write what kind of geometry you encounter there. Again, there are more manipulations needed, but let me just give you the spirit of things.
Thanks.
Yes.
Can you just go to the board how from this to define J? Because I think you said it in words, but
So J is the following. So you accept this functor, right?
Mhm.
So now plug in here this object along the second multiple. And then you obtain a functor from here to here. That is J.
oh, I have accepted this arrow. What is the arrow to which tree?
Again, so look at this arrow.
Yes.
What I said, that the essential image belongs to, well, okay, wait. There exists a unique arrow like this that makes the diagram commute. That is to say that this composition takes values here because it's a full embedding.
Okay.
So that's my horizontal arrow, and then I plug in delta here and obtain functor from here to here. That's my J.
Okay.
All right, that's it. That's the local functor. Now let me tell you the kind of global geometry you encounter when you want to prove the commutation of the left facet. So this local geometry looks as follows. So
You can't cook it at the fuel.
no, because there's also Sam's equivalence. You have to go from
Yeah, so
up to that. So I didn't want to go there. It's like you have to do something else. So the kind of global geometry is the following one. So we have, so we have bun P minus that projects, and it's convenient to use not P but P minus exactly because of this, because we have Whittaker category is defined using the positive Borel, and it's nice. The interaction is kind of nicer when with the negative parabolics. So this is exactly the diagram of the theories in just in stock. So here, Bentley's quantification. So this is a proper map. So then there is Bungie. Here there is this one n row of omega, which was introduced at the very beginning in Sam stock. It's this step using which we define the vacuum contrary functor. Vacuum contrary object. So this projects to the point well, also to A1. So what you have to do, you're pulling back, you're pushing forward the means of the a proper map, which you should pull back, you tensor up by the inverse image of the exponential, it integrates. So, however, because it's proper push forward and should pull back, here there's base change. Right. This product. In other words, you pull back, you shrink extend, you pull back, and you integrate against time. And now it comes kind of middle that, well, inside here, there is a open subspace which comes outside of space. And it's defined as follows. So what is the fiber product? So it's a G bundle equipped with a reduction to N and a reduction to P minus, at least at the generic point of the curve. And the exhaustive of space is the condition that the two are orthogonal, transversal at the generic point of the curve. So like mutual position of reduction to N and P minus are given by Brouillard theory, and you're saying that at the generic point of the curve, you hit the open Brouillard cell. So the point is that because of the presence of this non-degenerate character, only the restriction to the disaster of space will matter. So you will have to do pull back, push forward, pull back, restrict to this disaster of space and then integrate. And the disaster of space is closely related to this geometry of Langlands Langlands. So you see this local decay functors after you localize restrict disaster of space. So that's the picture. Again, we'll have a lengthy Q&A session, and I'll be happy to say more words, but like that's kind of the general, that's the flavor of things. That's the kind of geometry that goes into this picture. Well, in real life, yeah, poles. I mean, you just decorate this picture a lot, but like in essence, that's what it is. All right.
So let me just repeat what Dennis said. So there's this diagram, you want to prove that it commutes. And what happens? So if there's two things. So first, it's kind of hard. You might think it's kind of hard because it's like infinite dimensional geometry that's going on with these asymptotic onions, maybe, and you use some intersections and a little bit. Then this is explaining that there's another way to compute these things, and it's using, in some sense, bread and butter geometric representation theory about some quasi-map spaces. And if you're a homotopy theorist or something, you might just believe that these kinds of things, there's a well-developed science of how you go about them, and it lets you do the thing that it's saying you can do.
All right.
Could you repeat what curiosity diagram? What diagram you want to prove it?
The left facet of the coffin. Imagine the orbital line here. The head is here, you kind of made it already here, but you can keep it sticking out one that lid. So this is the geometric time line, okay?
Who is it?
What?
Who is it?
The geometric line. This lid. I'm doing this.
What's the functor from repo G chat to repo M chat?
Invariance with respect to input radical of the parabolic. That's the natural functor.
I mean, functors so these functors are lattice symmetric monoidal?
It lacks symmetric mobility, hence it lacks factorization. Okay. Correct. So that was all about the computation with ice. So now we'll deal with the computation with constant terms.
Just to repeat what Ben said, lax factorization is the same as factorization.
Sorry, it's factorization. Sorry, it's lax unit. Okay, it's lax unit.
The factorization things behave like lax.
Yeah. All right. Okay, so now we want to show the computation with constant terms, and we try to do the same thing. I'll just reverse. So I'll reverse the direction of the arrows. So this will be constant term. Let's call it. This makes it go. And you can look. So this will be spectral constant term functor. And I'll also erase this because this was all right. And so you want to play the same game. So again, I want to show that kind of the bottom lid commutes, and so okay, I erased quasi-coherent. Let's do the quasi. We'll have a problem here. Even with quasi, even with quasi. So yes, this functor is fully faithful. So it will be enough to show that the bottom lid commutes after you post-compose with this. And you want to use the same similar idea. You want to use some kind of functor here to make this commute, but it won't work. Problem is that like this commutation of global and local functors, well, not everything that you want to commutes. Yeah. So and here there's no language reality involved, which says we are purely the spectral side. So what you're doing here, you're taking you're applying the constant term functor, and then you're applying this functor of what we call gamma, and you might want to express it as first apply gamma and then something, and you can't, it just doesn't work. So this idea fails. So we have to do something else. And neither will work here. So like there is no local functor with some kind of fix that will make this right lid or left lid commute. Okay, so that doesn't work, and we'll try something else. Yeah, go ahead.
Just to give a feeling to that, imagine you took a skyscraper sheet of some local system, you load such check, and you were trying to track through this thing. Maybe it was an irreducible local system. So it goes to 0, you do this constant term spec, and then you wanted to have some kind of local kind of thing, or some factorization knowledge kind of thing, or something that essentially was that the local system is irreducible or not, and it's just very hard to imagine. It doesn't really fit in how it's like.
So instead you do something else. What you do, you use what Nick told us about this morning. So here we attempted to characterize the Langlands functor by how it behaves vis-a-vis this coefficient of gamma functors. We'll now use the characterizations that was supplied to us by Nick, namely that it actually can be characterized also by continued localization. And that's something that will work. And we'll draw a different cube. So position it slightly differently. Yes.
I really don't like how the guy's cube is staying.
Okay. So let me again say what we want to show. Again, I'm looking at the cheat sheet because I want to know the position. This is my constant terms. This is my spectral constant for the function. The Langlands function for G. This is the Langlands system for N. So again, this is what I want to show. But instead of trying to map to this refugee check runs, I'll hit them from below. So we'll use localization. So this is loc G. This is our monogrammic opers. This is the functor that was introduced by Kevin, this spectral functor. And this is our favorite capital E.
I'm also worried. The top diagram in its good form, no one ever said what I feel like most maybe in the students say the most important thing is just calculate local language functor does side and center. That's the whole point is through the bottom face of this.
In the previous good form.
In good form,
Yes.
that was the upshot of the whole discussion. Was that
Yes.
you deduce the commutation of the bottom face from the commutation of the other 5 faces.
Yes.
Yeah.
Okay, so say, right? Say it didn't say. Just. How to say it?
No, can we say it?
Yeah.
Am I?
No, just.
It's possible I was just spacing out and didn't say it. But
You may use that level. Now it's good.
anyway. I think the thing Dennis is trying to say is that color and multi-faces, except the bottom one. Playing color chop, not being there. But this one commutes, that's the theorem.
That's what we want to do.
That was what we wanted to prove. And what does that say? It says that you do Eisenstein series and then the Langlands functor, give or take, that's the same as doing the Langlands functor and then Eisenstein series.
Yes, but you said two things. You prove this can also be calculated with the repetition of Eisenstein series in the process. Well,
This is Whittaker coefficient of Eisenstein.
well, if you just look at the lower lid, just Langlands, there's no lower option.
This is Whittaker coefficient. Yeah.
Okay, so let me reiterate. Okay, so we proved this theorem, but the method of proof was this: that we, in the process, we calculate these things, and we calculate these things by applying coefficients on M and doing something local on both sides. So that's what we did. So that on both sides of language values, which is very actually close to the method of proof that Nick used. Again, so we this side lids of the cube, and just repeat one more time. We're computing Whittaker coefficient of Eisenstein series by some local procedure, both sides separately, and then we compare. And that's exactly what happened in Nick's talk. So he calculated both vertical compositions by some local procedure, some privileged homology, and if you compare it, he showed that they feel the same. We were doing exactly the same thing. Okay. Okay. I lost the thread. Both foot I lost the positioning. Right.
That was very good impact.
To derail me? All right. It didn't work. Isn't it not critical level for it? It's all critical level. It's all critical level.
Additional approach, yeah. You're thinking of?
Yeah.
Yeah.
Yeah. Very actually. Yeah. Right, this error space. So this is FLE. This is one for check. What do we have here? Let me write what's missing. So we have this, we have this. So now we want to show that the top lid commutes. So we have this arrow, this arrow.
What's the top arrows? Top face again.
So D1 by G, but the in code. There's one stop. Okay. In code log system. Yes. So again. Okay. That means all good, yeah.
But you want to start. What does the top face say? Just
The top,
read it out loud for us.
the top face is what we want to show. It's the commutation of length functor with constant variables. That's what we want to show. So what we want to show is that want commutation with the template. And so what do we have so far? So so far we only have top face and the bottom face to commute. So this is exactly the content of exactly the content of big stop. So what we want to do now is to construct these arrows and to show that the bottom lid commutes and the side lid commutes. Once we do that, we'll then we'll see that the 5 facets commute. Therefore, you can therefore we can uniquely recover no. So here's the problem. So what was the logic features? Yeah, there was something I was just saying. So the logic features was that this piece level of quasi-code, this logs this quasi-code to check embedded fully faithfully into the local category. Like, how do you know that this is large enough to force some kind of commutation? So let's suppose I had 0 here. If everything on Earth commuted, I would have proved it. So here comes a thing that will be explained in more detail actually tomorrow. It says that this arrow is not exactly quotient, but it's has strong enough validation property. It's actually quotient of any quasi-compatible stack. So that if you want to show that the upper lid commutes. The domination property will be such that if you throw that this upper lid commutes with after pre-composing this localization functor, that it actually commutes. It's close enough to being quotient so that you force the commutation. So therefore, let's assume that this property, therefore, it's enough to construct these arrows and to make again the side lids and the bottom lid commute. Ishan.
Yeah. So from the Eisenstein meeting?
From
the Eisenstein meeting?
Yeah.
Do you not get a Beck-Chevrolet comparison?
Yes, and it's
then-
very bad.
and
We'll
then
come back to
compare
it.
that-
So you have back-Chevrolet national transformation, and we'll come back to it in 15 minutes. It's a bad Chevrolet.
So this localization, I mean, how essentially subjective, for example?
If you restrict your G to any quasi-compactable substack, it becomes a quotient functor.
Okay.
But the point is that both arrows, both surfaces of the diagram, if you want connected component by connected component, the only field given quasi-compatible. So that's the whole idea. So that you know that the arrows commute enough for you to restrict the quasi-compatible. So that's why this kind of domination is enough. All right. So,
But maybe like how I mean, restricting to quasi-compact opens, like how much, like how few things are seen by quasi-compact opens.
as I said, so
I mean, I know that the argument will work, but like in general, I mean, how many D modules are seen by quasi-compact opens?
it's a great question. Let's discuss during the Q&A.
Okay.
So this non-quasi-compacted 1G is a serious issue. You're definitely not seeing everything. We'll discuss it later. All right. So now, what are these arrows? And again, so for the next 5 minutes, I'll just wave my hands because I mean, so developing this theory takes like 250 pages. I think G53, that's most of the work. So this functor is called also EFK functor of the smoothie, and this functor is called EFK functor. So let me tell you what they are. So Jacquet smoothie is really what Lin called BRST, and it's a functor that already appeared with semi-infinite homology with respect to loops into the radical parabolic. Point is that if you take the semi-infinite homology and apply it to representation of loop algebra T, if you kill the uniform radical, the Levy quotient acts. So that's why it's not just the vector spaces, but it's functor from Cavalier-Lucid category for G to Cavalier-Lucid category of Levy. And so this is really what this functor is, and the commutation of this of the left facet. Note that this left facet does not involve Langlands reality. It really takes place just between G and the Levison loop. This is the particular case of what Lin proved. So in fact, he actually proved this thing. So toward the end of this talk. So it's exactly his pattern. So J opers. So it's supposed to be some kind of functor from monodromy-free opers for G check to monodromy-free opers for Levy check. I leave it as an exercise. Try to play with it. Just try to see if you can concoct some kind of functor that goes from here to here. So it will be some pull push.
First, the J is in fair.
Pardon?
The K is in fair.
In terms of Roche? Yes. So when you do this, it needs to be fixed in the neck way. And also, so I'm describing the local functor, which also always has to be fixed in the way that they can then explain it. So as a local functor, it's a pull push. So it would be opus monodromic frequency check. Will be question mark. And it's really kind of a very nice exercise. Just try to invent it, and you'll learn a lot. And we'll push. And once you discover the commutation of the right lid, again, there's no Langlands. All happens on the dual side. Will be checked. It's interaction between group G check and its Levy subgroup. This commutation is very akin to what Kevin explained to us with this last talk yesterday. So, at the end of the day, it will be the fact that global sections, the functions on the scheme of global sections, some find the scheme will be given by some factorization homology. Yeah, I read it as an exercise. Actually, it is really an exercise after what Kevin explained to us. Okay, and where does this leave us? It's what's the idiom that is in what ditch? What's the nice expression? Lurch, yes. Can one live in the bad lurch and the lurch you bad and good? No, it doesn't lurch it. Lurching. So what are we left with? it's the bottom lid. Namely, so here you have KLG going by means of its FOE to input star monochromatically opers. Here is KLM. This is JK functor for Kotsmudi. This is input star monochromatically opers for uncheck. There is this functor JK functor opers, which I left as an exercise. And here is this FLE for M. And the bottom lid says that, so this is the bottom lid. So should commute.
Yeah, you put this, then literally put this diagram, please, then in particular the thing with flexible.
Yes, if this, so the fixes are functorial in terms of local operations. The problem is that this is super hard. That's not 100 pages. It's completely local equivalence could have been done like 30 years ago, given the tools, but like it's a hard theorem, like local representation. It uses a lot of factorization methods that were explained in the previous lectures. Hard work, but has been performed. All right. Unfortunately, I need another 10 minutes to summarize things. So we've mission up, so to say, we've proved that our Langlands functor commutes with constant terms and Eisenstein series. So we are in great shape. All right. So the cubes were only meant to show that the functors, Langlands functor commutes with Eisenstein series and constant terms. So that's what I explained. Remember, so I want to show that upper lid commutes have three composed with this functor. It's not to show that by the domination problem that found is the same as found. At the start of the cube, we all the facets commuting then goes to the report commutation list. Well, the same combination probably I thought this is the type of you're exactly right. It's not the type of it's not the entire temper part, but I said it's a quote you have to restrict to any quasi-compact elements of that, but that's enough. Turns out. All right. So
Can I just make one comment about this? You said it out loud earlier, but just if just for a second, if you imagine like maybe in the case of a torus going to a single connected component inside of this bond T. So that's just some pullback to a single component of bond B, the mapping down to that single component of bond T, and that single component of bond B is quasi-compact. So it's sort of manifested the case by component. This functor only depends on the restriction of the G module to a given quasi-compact domain. And then what that is saying is that becomes really a surjection, and it's really.
all right. So now in the remaining, so I'm sorry, I'm taking 7 minutes, but we have a Q&A session after. So corollary. The Langlands functor admits a left adjoint. So proof, let me assume by induction that you know the assertion for proper Leibniz groups of proper parabolics. So here I'll give you a proof. So consider the following general paradigm. So first of all, you have a functor from C to D, call it F. For a given object in D, you can ask it. So the L left adjoint is always partially defined. It's a question of certain functor being co-representable. And so for a given object D, you can ask if the left adjoint is defined on it or not. Also, if you show that the left adjoint is defined on the generating set of objects of D, then it's defined. It's easy to see. All right. So want to show that Langlands functor is defined on the generating set. So here is general paradigm. So suppose you have a functor from C to D. And suppose you have another pair of categories, C1, D1. So the functor F1. And functors like this, so we call this IC, and this functor ID. And suppose that the following happens. Suppose that this functor admits left adjoint. And suppose that all, so here's IC. And suppose these functors also admit left adjoints. Lemma, in this case, the left adjoint of L is defined on the essential image. Image of IDL, and moreover, so that this commutes. And no surprises here. If this diagram of right adjoint is past the left adjoint is commutes, but here I'm saying that left adjoint is defined in the essential image of this. So now we'll use it immediately. Oh. Not the race. We want the race.
Your general statement, what are the hypotheses on?
So I admit that I see an idea admit that the units. And F1 admits that the proof exercise. So we'll apply the two circumstances. So one is, so here is D mod on G, mapping the means of the Langlands functor to int code with log CSG check. So here is our functor coefficient G with G. And when we check run, this is the functor in check spec. And this is the customer like equivalence. But we know that these functors admit left adjoints. This is functor A. This is our log spec. So we apply first this lemma to this setting, and we obtain so the Langlands functor L is defined on the essential image of this functor, but we know what that is. This is just quasi-code. Quasi-code logs this G check as sitting inside. Yeah. This is no surprise, but if you remember how, like in my review, how I defined the Langlands functor, in fact, I started with this guy. So like I started with a functor for quasi-code to D of 1G, which was exactly defined at this diagram that commutes, that makes downward facing diagram commute. All right.
And also just again, you're saying, so this LG course obviously admits a left adjoint. It's very easy to see from the construction. And then this part of the nature of this renormalization game is it's very hard to see. You can't just deduce formally. It's a lot of work, which you just were explaining, in order to see that LG itself actually admits a left adjoint.
And let me also, so let me just emphasize this point one more time. So what we've proved so far, or we'll finish it in the second proof that LG admits left adjoint. So what is not the thing does, and we usually use extensively tomorrow, so this is the functor. So this is d mod d. It makes this diagram commute. This is LGL. No. What's G check? And here this is G check 1. This is localization step. G check. This is has much like equivalence. So remember again, the Langlands functor makes the diagram commute when we have a couple of basic errors. The rule makes this diagram commute. At this point of the proof, we don't know that if we change the error, the diagram will commute. We don't know that. And it's again, it comes at the very, very end. We don't know the Langlands functor makes commutes with downward basic errors. We know this functor comes with downward basic errors. So if we knew that, we would have terminated much earlier. So that's what we have so far. Now let me apply this lemma one more time. In the following situation, so I have d mod 1g, but now here I have d mod 1m. The functor will be constant term star of g into milk of the check. Here it's constant term spectral equal milk. This in check. This is the functor Lm. We apply this lemma. So here we reflect the joints. This is I's streak. This is I's spec that we just talked about. Apply the lemma, and you obtain that. So obtain LGL is defined on this essential image of I spec. Again, for a proper lady, I'm assuming that we know everything for proper lady subgroups. And moreover, it makes the following diagram complete. We know down G. This is one LGL. Milk. Let's see the check. Remove one M. See. Sleek. Development L. All right, so that's what we have so far.
But the practice is less of an define quasi code.
Yes,
That,
by definition.
yeah, that's just by definition.
Yeah.
Great.
The fact that it's defined on
Yeah,
this guy is I'm using that diagram with
Yeah.
commutation and the functor of constant, which is very expensive.
Yeah.
200 pages.
And maybe one more comment in this direction. So on the first day, Kilo asked, this construction of LG, you never used info milk, but then you just used info. And the answer was yes, you could have used info. But
No. Let me just say one more phrase and you'll say. Okay, let me just say one more phrase. So now we finish the proof of the lemma. Where is that? Where is the lemma? Where? No, not that lemma. So there was a corollary that said that just LG was by the joint. You erased it.
yeah.
Yes.
You
Somewhere in the middle.
Yes. Okay. So we obtain that LG is defined on the essential of fuzzy code, but also the essential images ice. Now finally, it's a lemma. This is kind of the main kind of input. Why it's indeed in code, so that it's intermittent. of loxus G is generated,
I did this in.
yeah, by Q loxus G check and the essential image of this Eisenstein, as mentioned by Justin. So therefore, it's defined in both these guys, and therefore it's defined on the entire thing. So that's so therefore we prove the corpus. So the left adjoint is defined. All right. Okay. 5 minutes.
Sorry, can I finish my sentence?
Yeah, please. Yeah.
No. Akil asked, why couldn't you just use info as the target? And this statement would have been false if you had used info as the target.
Yeah.
Isn't that-
This statement was false.
Well, the statement, the theorem said that LG against the left adjoint could be false.
Yeah. Absolutely. All right. So now definition. So we take D mod bungee eyes. It's the full subcategory generated by the essential images of our streets by proper parameters.
Okay, I have a question.
Yes.
So in that argument, were you using induction to know that Ln as a length function?
Say again.
So in the argument,
Yes.
the upper body, were you using induction? So that
Yes, I assume that the upper top horizontal arrow exists. So I was assuming geometric Langlands for the Levy. In fact, I didn't have to, but just for simplicity, I did it.
And
So-
it's the Q code with the,
Pardon me?
if the Q code is the cos theta part,
Q code again.
the cos theta part, you know,
Can you say the full phrase again?
it's the Q code LSG has the cos theta part.
Yes,
in
yes.
the
I'm getting there now.
But it's the temporary part, no.
This is what I'm saying. No, I think that's. Say it.
QPO is the cuspidal part, and I'm saying no, QPO corresponds to.
Q code, the tempered part. You'll see the cuspidal part in a moment. Give me 1 second. So this is. It's a full subcategory. It's generated by compact objects. And therefore, its embedding admits a right adjoint. And by definition, if you recall the definition of cuspidal subcategory, it's exactly the kernel of this functors. So cuspidal subcategory is exactly the right orthogonal to what's generated by Eisenstein series. And so we have this short exact sequence of categories. So right. I'll denote this functor by E, and this is I denote this functor by EL. So E is the embedding of the cuspidal subcategory, and EL is its left adjoint. So and it is what it is. So we have the short exact sequence of categories. Similarly, so definition, we take intco. I'll answer your question in a moment. Nil loxis G check. It's whatever is generated by spectral Eisenstein series. I don't want to write it here. Wait a second. Where is it? Neighboring board here. Definition. Loxis G check. Eyes. It's the total generated by the essential images of the functors stabilized into its functor for proper parameters. And so you have the same pattern, intco boxes G check eyes embedding into the right adjoint for intro nil boxes G check, and here we call it E spec L. E co nil boxes G check cusp. But here you are in geometry, and it's easy to see that we know what these things are. So in fact, pardon? Pardon? No. So I claim that this category is nothing else but you take int code log sys dcheck with set theoretic support on the reducible locus. You take local systems, you look at those which can be reduced to proper parabolas. And this is just the full subcategory in here, distinguished by this support condition. And this guy is also its int code built on the open part, which is irreducible local systems. But with this, assume that local on irreducible locus, nil equals 0. So this is just quasi-total. And under this identification, this E spec is the functor that we call it J spec lower star. So I'll denote by J spec the embedding of the irreducible locus. And E spec L is J spec upper star. Again, J spec the embedding of the irreducible locus. And so let's see what we've got here. So here we have int code log sys gcheck nil. We have our Langlands functor with its left adjoint. And it makes everything commute. So it induces what we call int code nil log sys gcheck. I'll write red. So it induces functors. I call it eyes. Right. So both these functors commute with the embeddings and projections to both these subcategories. So everything commutes. Log sys gcheck irreducible. And it will be J spec upper star, J spec lower star. And again, I want to show that these guys are mutually inverse equivalences. Let's see where I can get with this using the induction hypothesis. Let me now input geometric Langlands for proper Levy subgroups and see where it gets me.
What's the relationship? Hospital is tempered.
Hospital is contained and tempered. And it's reflected on the geometric side, but on the spectral side by the fact that here I have quasi-cove. So
J lower star.
So yes. So on the cuspidal part, which the spectral side is the irreducible part, inconil is quasi-cove. Therefore, the cuspidal part is contained as quasi-cove, i.e. it's tempered. All right.
Thanks.
Yeah.
I missed the part. How do you define E and sorry, no, how do you define the Bungee cusp?
The right orthogonal of this.
So we need some circularity.
No. So it's a full subcategory. It's embedding admits a right adjoint. Cusp is just the kernel of this right adjoint. Equivalently, it's all those objects here which are right orthogonal objects here. Subduality will be tomorrow. No subduality now.
Which again, concretely, hospital means annihilated by all constant functors.
Okay.
Right. So, input geometric Langlands for proper Levy subgroups. So, theory. LG, L eyes LG eyes are mutually inverse equivalences. The big achievement of modern science will show that at least by adopting semi-simple rank, we'll see that these functors will be mutual inverse equivalences. Let's do it. So what do we have to show? We have to show that unit and counit functors with conjunction are isomorphisms.
Wait, what's the definition of this LG?
So I'm saying that from this theorem, so compatibility of Langlands functor with constant terminalizing series, it follows that both these functors preserve this, send this a category to here. So that's what it says. This and nothing else. All right. So we have to show, let's say, from units of the junction, we want to show that F Langlands functor I's well, F is an isomorphism of any object. So this kind of thing is not the proof for generator. Let's do it. So the generators, so it's not to do it for I's. It's not to show that this natural transformation is an isomorphism. So let's do it. So what did we prove? So the first part today, I proved that this is isomorphic to LGI's. No, it was at the end. So like this that LG left adjoint commutes with Eisenstein series. So I proved that this is the same as I's. Does it make sense? No, it's Eisenstein. Yes, it's Eisenstein. So this is I's sheet L M. Right. L M. This is the commutation that it's still with that word up there. And then we also prove that Langlands functor commutes with Eisenstein series. This is the same as I spec LM pool. And now we know that by induction, this is the unit for the junction of isomorphism L step. So we've shown that the right hand side is isomorphic to the left hand side. Great.
I wonder if Ishan has any questions.
Ishan, do you have any questions? So we've shown that the right hand side is isomorphic to the left hand side. What we calculate the right hand side, we swapped Eisenstein series with left adjoint, that blackboard, and then we swapped Eisenstein series with the right adjoint, and we arrived to the left hand side. Yay! What? Exactly, we don't know. So you asked me if like if that Chevrolet gives me a map in one direction.
I wanted to know if they were the same two marks.
Exactly, we don't. And probably they are not. So it's very likely they differ by scalar. But at this point of the proof, we don't know that the scalar is non-zero. So we don't. So yes, the left-hand side, right side is more left-hand side, but we don't know that the more that we want to be an isomorphism is an isomorphism. However, we prove it in other 100 pages. So you have to do another Mambo Jumbo we prove. And also, this is the unit of the junction, you co-unit of the junction, the same kind of thing. Same problem, we prove it. So it's a true theorem, it's proved in the end of GLC3, but so if you see that if you over GLC3, there is like 1/3 of it is devoted for stop enhancement. This enhancement is exactly its own role. All right. Last minute. Let me see where I am. All right. So we've shown that these guys are equivalencies. We want to show that these guys are mutual equivalencies with mutual inverse equivalences. Therefore, we've reduced the whole problem to showing that these guys are mutually inverse equivalencies. So we've reduced, like kind of in the best case scenario for automorphic forms, we've got rid of Eisenstein series. We've reduced our problems to the cuspidal part. Cuspidal part happens to be technically the easiest, but ideologically the most complicated. So we don't understand the technical. We don't know what's in the cuspidal functions. because we can't reduce them to smaller rank. Again, we've reduced GLC to showing that this pair of adjoint functors is the equivalence, mutual equivalence, and however, we already can give a proof for GLN. So for GLN, you can finish now. And as for this,
based on.
so we have P mod Bungie cusp. Rounds with verification conference. Int code, quasi code, losses, HF, irreducibles. So those embed JSPEC fields are model Bungie. And here, info, no, once you check, and so here it goes, suite of the line. Mix, G1. These are equivalent. So we already know that this functor, gamma, which I expect, is fully faithful on quasi-code. Here we are in quasi-code, so this functor is fully faithful. And now there's a theorem, it's very old of 15 years ago, that says that on the cusp of part 4G equals GLN. This functor is fully faithful. So that already gives us that this functor is fully faithful. Everything commutes, this is fully faithful. Again, this something we know for GLN a priori, something that we have to fight for really hard for other groups. This is fully faithful, this is fully faithful, therefore this is fully faithful, and it's easy to see that is a separate argument, essentially subjective, not the.
So let me make my talk this morning. So the group of PGO2, I was saying that the hospital modular forms, you can obviously recover them from the Q extension. And the argument in the GL2 case that the left arrow is fully faithful is just essentially that saying
It's Fourier transform.
it's just Fourier transform.
Nothing else.
Yeah, and for GLN, there's like a known method to the PHF feature theorem that generalizes that kind of thing. It's a little non-obvious, but for those things are known to fail in related.
All right, so that's the end of my talk.